Hello friends, welcome to the channel for another video about supply chain analytics. Today we will build a simple methodology to design a robust supply chain network using Monte Carlo simulation with Python. This video is following an article I published a few months ago. I have added the link in the description. Supply chain optimization makes the best use of analytics to find an optimal combination of factories and distribution centers to produce and sell products. From the demand side, you get the sales forecast per market in million units that will drive your decision. Moreover, you need to consider the supply constraints, such as the minimum quantity and delivery time. And finally, your target is to minimize the total cost. From a supply side, you must consider the production capacity of your factories. You can choose between low and high capacity plants in our example. But also the fixed cost that will depend on the location and the factory size. And finally, the variable cost that will be mainly driven by HR costs. That's why they will depend on the location. The question is, where do you need to put your factories and which size to fulfill the market demand at the lowest cost? This analysis will be based on an actual project I conducted. I have shared dummy data in my GitHub repo. Let's conduct a quick exploratory data analysis. You start by analyzing the demand per market. Japan and USA are driving more than half of the demand. But you also have two types of factories. Low capacity, which makes 500k units per month, and high capacity that make 1.5 million units per month. Your choice of manufacturing locations will impact your production costs. The fixed cost, depending on the location and the factory size. It's quite interesting to see that a high capacity plant in India has lower fixed cost than a low capacity plant in US or Japan. And you have the variable costs, mainly driven by the cost of workforce. They are the highest in Germany and the lowest in India. If these were the only parameters, the choice would be easy. You outsource to cheap labor and low fixed cost countries. Indeed, let's imagine you need to plan your production for a specific market. Here we take the example of the US market. You need to produce 2.5 million units for a total cost of $67 million. The production is shared between a large factory in India and a small one in US. We can clearly see that the production cost per piece is way lower in India. However, for India, you need to add the transportation variable cost to ship your product from India to USA. Therefore, we need the support of linear programming to take the decision. Indeed, the solution designed yesterday can be obsolete tomorrow, especially when conditions are disrupted. We can take this beautiful example of the surge of sea and air freight costs during the last 2 years because of COVID. So, let's formulate the problem. Your objective function is the total cost of production. We want to minimize it. Decision variables are Boolean variables allocating production facilities to each location. For instance, high capacity or low capacity or no capacity. Then you have the constraints. The first one is that the supply, so the production output, needs to be higher than the demand. The second constraint is the limited production capacity per plant. And the final result will be a list of factories opened with the output volume for each of the market. So, if I want to summarize using a less mathematical way, you are pushed by the market driving your demand. You have potential location available for production with different types of size. Your target is to minimize the total cost of production per piece. The first output of your model will be the footprint of plants all around the world. And the second output will be the goods flow. So factory A producing for market X and market Y. That's a conventional way of doing a network study. So let's start by presenting the initial solution. So using the parameters presented before, where do I need to open my location? I need 1 low capacity plant in India and 3 high capacity plants in Japan, Brazil and India. What are the manufacturing outputs by factory and market? This is a nice Sankey chart to show you that India is the biggest hub that is fooling half of the US market, and also India and Germany. We can see here clearly that the model uses India as a huge manufacturing hub at its maximum extent, and the same for Brazil. But are we considering the demand variability? Indeed, is our solution robust in case we have plus or minus 5% of volumes on some market? What we see in this chart is that the current footprint is close to its maximum capacity, and it's hard to see robustness in our solution. Therefore, we'll explore another method to improve the solution. We start by generating 50 scenarios assuming some variability in the demand. For each scenario, we generate the optimal footprint that will minimize the costs. We analyze the results. What are the different footprints proposed by the model? We then decide which footprint to take to have the most robust network. Step 1. We generate the scenarios. I basically took the initial demand level for markets and I assume a normal distribution with a reasonable standard deviation. This variability can be seen in real life, especially if your business is seasonal. So this is a very good exercise to assess the robustness of your current footprint. Okay, so now that we have built our 50 scenarios, let's run the model for each of them. This chart is drawing the results for each of the 50 scenarios. On the y-axis, you have your potential facilities that you can open or not. If it's blue, that means it's open. And on the x-axis, you have the 50 scenarios. I included the initial one so we can compare the results with the generated one. On the left, you can find your initial solution with a low capacity plan in India and 3 high capacity plans in India, Japan, and Brazil. Good news! You can also find this solution in other scenarios. Moreover, some other footprints are quite similar, like the yellow one, that is only adding 1 low capacity plan in Brazil, probably a scenario where the demand is a bit higher. What is quite surprising is that you have also very exotic solutions, like this one showing all plants open, probably the maximum of the demand. Let's not forget that the normal distribution may bring outputs lower than the average but also higher. In that case, I am quite sure that several countries are showing demand peaks, so that's why we have such an exotic scenario. And then we have the exact contrary for the scenario 46, where only 1 high capacity plan in India is enough to meet the total demand. Let's plot these results to have a better understanding. On the left, you have a donut plot showing the split of the results. We are talking about a vector of Boolean value representing the optimal footprint generated by each scenario. The initial result is representing the majority. But can we say that it's the most robust? It will depend on your definition of robustness. If you want to avoid stockouts, which means the market demand not fully met, then you can consider that you are close to the maximum robustness with this solution. If you want to play it safe, you can add the low capacity plan in Brazil. But is it the most optimal solution? For this, you'll need to simulate the impact of cost stockouts on the 50 scenarios if you use this footprint. For this, you can bring additional constraint in your model, for instance adding some penalties if the demand is not met, instead of putting a requirements of minimum supply. At this stage, you've built a tool that will help you to improve the robustness of your solution, and it's just the beginning of bargains, discussion, simulation to take you to the final decision on which footprint meets your business needs. I hope this video gave you the keys on how to use the Monte Carlo simulation for supply chain optimization. You can find the full source code with dummy data in the article link in the description. If you need additional clarification or support to implement your code, feel free to share your questions in the comment section.